plus delta yj plus delta zk is our change in the r vector. And is nearly tangent to the surface defined by r of r theta. Now, we haven't even really shown that this vector function r of r theta defines a surface. We'll see that shortly. As far as you know, that might define a curve instead of a surface. Although if you think about it, you'll see that this should define a surface, that this r function here should define a surface relative to the xy plane. That is a surface in xyz space. Now specifically, delta x is approximately equal to x sub r delta r. Delta y is approximately equal to y sub r delta r. Delta z is approximately equal to z sub r delta r. So the vector, this vector becomes xr delta r I plus yr delta r j plus zr delta r k, and that is our approximate delta r. Okay, we'll say it's approximate. And if we factor out the delta r, we see that this is just xr I plus yrj plus zrk times delta r is approximately equal to the delta big R. This expression is nothing but our derivative of big R with respect to r. And our delta big R vector is just this vector here. And this vector is seen then to be a vector. Let's go ahead and shade it in blue and label it in blue. That vector is r sub r delta r. Approximately. Actually, that's not approximate. This vector is an approximate tangent vector. Again, approximately tangent to our surface. Now, a little more briefly, I'm simply going to state that a small delta theta implies a small delta x, delta y, and delta z. Completely analogous to the statement we have here. It's very clear that if r is a function, the big R vector, if our vector function r is a function of little r and theta, then a change in theta is going to give us a small delta x, delta y, delta z, where delta x equals x theta delta theta, delta y equals y theta delta theta, and delta z equals z theta delta theta. And I'm going to leave some dots here, with the dots parallel what we say over here, which tells us that r sub theta delta theta is a tangent vector. And there's no reason to assume that this is going to be in the same direction as this. Matter of fact, we can see that with certain assumptions, this direction is different. Not only that, but we're going to have a picture now in 3 dimensions where we have a certain delta S in the plane, a certain displacement in the plane due to r, another displacement in some other direction that'll depend on the nature of our functions, x of r theta, y of r theta, z of r theta. Won't necessarily be a perpendicular direction. Above this point we have the vector r sub r delta r. Above this point we have another vector r sub theta delta theta. So we got an r sub r delta r and an r sub theta delta theta. This region of our coordinate plane is then going to lie below a parallelogram up here in 3-dimensional space, and the area of this parallelogram is r sub r delta r cross r sub theta delta theta. And of course delta r and delta theta are simply numbers which can be factored out of the cross product. Leaving us this expression for the area of this parallelogram. We'll see in another clip how this relates to finding the total area of a surface over an r theta region.